is the second derivation, number density of holes. It is going to be very similar to the first. So we saw the previous derivation we saw was the number of electrons in the conduction band. Now we are going to see the derivation for the number of holes in the valence band. Now intuitively we know that it's going to be equal, because every time one electron moves, one hole is created. So if I have x electrons, I should have exactly x holes. But we will derive this using a similar approach, and we'll get an expression for the number of holes, and then we'll be equating both the expressions and trying to infer something else. But anyhow, we'll go with this derivation now. So the number of holes should be, the holes are present in the valence band first of all. So the limits here will be from minus infinity till EV, where EV is the topmost level or the last level of the valence band. So if you remember, for the conduction band, it started from EC, the lowest level of the conduction band, and went up to infinity. For the valence band, it starts from minus infinity and comes up to EV, EV being the topmost level of the valence band. So under those limits, again the number of energy states into probability that they are vacant. Why vacant? Because we are talking about a hole, not about the existence of an electron, but about the absence of an electron in the valence band. So it should be integral from minus infinity to EV, g of E into 1 minus f of E. Because f of E is the probability that an orbit is occupied by an electron. So a probability that an orbit is vacant or an electron is absent would be 1 minus f of E. So again, before starting the actual integration, let's find out what 1 minus f of E would be. 1 minus 1 by 1 plus e raised to e minus ef upon kt. You take the LCM and perform the math, you will get this expression. Again, you are dividing both the numerator and denominator by e raised to e minus ef by kt. You will get this term. Again, this e power term is very high, so you ignore the 1. This is the final expression. You get e to the power e minus ef by kt. So this is just simple math. We in the previous derivation we took f of e and we did some approximations. Here we are taking 1 minus f of e, we take the LCM and compute the term, and then we do the same approximation of dropping the 1. This is what we get. So this is what we are going to take as 1 minus f of e. Again, moving on, integration from minus infinity to EV, g of e into 1 minus f of e, which is, this part remains the same. Integration minus infinity to EV, root e to the power e minus ef by kt dE. This is what we have so far. So now again we have another standard integral given to us, and this expression pretty much resembles the expression inside, but the limits here are from minus infinity to EV. Here they are from 0 to infinity. So again we need to perform some transformation of limits. So what we do is, we will first make this minus infinity to 0, and then we flip the limits and we apply a minus sign. So what we do is we subtract EV everywhere, like we subtracted EC from every term in the previous derivation. Here we will subtract EV from every term. It becomes, this constant part remains the same, minus infinity to 0, because EV minus EV becomes 0. Here EV minus e to the power e minus EV plus EV minus EF by kt dE. So what you have to notice is, it is supposed to be minus infinity here and e minus EV here, but because we need to bring it between 0 and infinity, we are performing that flip. We make it 0 to infinity. This part should actually be 0 to infinity. It's a typo here in the slide, and because we need the negative sign, we make it EV minus e, because when you flip the limits of an integral, the sign changes. So integral from a to b of something is the same as minus integral from b to a of the same thing. So that's exactly what we are doing here. So initially when I just subtract EV minus EV, it will be from minus infinity to 0. Now I want to make it infinity, so what I do is I make it EV minus e here instead of e minus EV, and I flip the limits here. So this will be from 0 to infinity, root of EV minus e to the power, same thing, dE. So again we take out the EF and EV part because they are constant. This under root remains the same, e to the power minus EV minus E upon kT dE. Now if you compare this with this, this again should be 0 to infinity, it's a typo. So you compare this expression and this expression, you see that there is a correspondence where x is equal to EV minus E and A is 1 by kT. And the solution is given to you, again you substitute it back again, this is the expression you get. Again you club together all the constants and we name it NV because here we are talking about the valence band. So the number of holes in the valence band is given by NV e raised to minus EF minus EV by kT. So again we'll quickly recap this derivation. We wanted to find out the number of holes in the valence band. So from minus infinity to EV, which is the top of the valence band, we find out how many allowed states are there and the probability that they are vacant. So G of E into 1 minus F of E. So 1 minus F of E we first computed, we dropped the 1 again, and when we first took the LCM and added, then we dropped the 1. This is what we get. We perform the integration, and again to bring it to standard form we subtract EV everywhere, and then the limits are from minus infinity to 0. We flip them, we make it 0 to infinity, and this term which should have been E minus EV becomes EV minus E to account for the flip in limits. Then yeah, we have the standard form, we have the solution, so we plug it in, we group all the constants together, we call it NV e to the power minus EF minus EV upon kT.